Welcome to everybody this morning. Thank you for joining us. This is a HySeas III Consortium event or workshop put on to sort of talk a little bit about LCA analysis. If you don't know what LCA analysis is, you might maybe learn a bit more about it at the end of it. If you weren't expecting to hear anything about LCA analysis, then maybe you're on the wrong Teams call. We have a bunch of slides, as is normal in these things. We do encourage questions, and if you do have questions, please write them in the chat, and we'll probably deal with them sort of as it's sort of convenient for us to get to it. And we hope to also have quite some time at the end to have a discussion. This is genuinely meant to be a workshop. We want to have questions, we want to have discussion, so we'll kind of learn from each other. I'm Edwin. I'm part of the HySeas Consortium. I'm a naval architect, and I do a lot of stuff at the IMO. And I have with me Camilo Gomez, who's a research engineer at the German Aerospace Institute, who's a chemical engineer by training and has done a lot of work on LCA analysis for the HySeas Consortium. The HySeas, for those of you who might not know, is an EU Horizon 2020 funded project. That's the nod to the money that we got from the EU, which is looking at fuel cells on hydrogen-powered fuel cells and the integration of that in a propulsion train, and how that works in the wider context of a ferry. I'm going to kick off a presentation. Let me just start this. This presentation is being recorded, and it will eventually be edited and placed on YouTube for future reference. Let's go. So roughly speaking, the agenda today is an introduction to LCA, ISO 14040, where the IMO is with lifecycle assessment, and the HySeas III case study. So here are some guiding questions. Over the next few slides, we'll have a look at what is lifecycle assessment, why should we use LCA instead of other methods, and how would an LCA for ships be carried out in practice, and what the advantages and disadvantages of LCA in comparison with other methods. You probably all have heard of, in various contexts, what LCA might be, and the kind of main governing standard for it is ISO 14040, which is up here. Oops, sorry. And I need a pointer. LCA, life cycle assessment, LCA for short, addresses the environmental aspects and potential environmental impacts, i.e. use of resources and the environmental consequence of releases through the entire life cycle of a product, from all the way from raw material extraction, acquisition, through to production, manufacturing, use, transportation, use, end-of-life treatment, disposal, and so on. So this is the whole cradle to grave concept. We want to understand all of the environmental impacts from the start to the end. And the main applications of LCA are in product development and improvement. So you do LCA for a product and you sort of say, okay, it looks like this. Can we make it better? If we change certain inputs and certain processes, can we reduce the environmental impact in certain areas? It's also used for informing decision makers for strategic planning, priority setting, and actually public policy, which is probably a lot of where your curiosity comes from today. And so the outcome of LCA is to sort of broadly say to those making decisions what they should choose, prioritize, improve. It can be used to select relevant indicators of environmental performance. Should we only look at GHG or should we also consider if a product has consequences on water use, on toxicity, and so on, and which are the ones that matter for a particular product that we need to keep an eye on. And of course, you can use it for marketing. And these, by the way, are all in ISO 14040. It's not something we've made up, but these are sort of quite standard in the document. LCA is an iterative method. So you have 4 phases. You have the goal and scope definition. So goal meaning why the study is being conducted. And then the scope is what is not being studied, how it's being studied, when and where it's being studied. You then get an inventory analysis, which is the compilation of quantification of inputs and outputs. You collect all of the data about all the parts and the processes that go into your product or whatever you're studying. And then after inventory analysis, you go into what's called an impact assessment. So you evaluate the magnitude and significance of potential environmental impacts. Once you've done that, you can then interpret your results. This is all a bit abstract, so let's do it in a slightly different way. So your goal and scope could be an LCA of a car of a particular type, assuming a use for a number of years, produced in a certain country, etc. Your life cycle inventory then looks around, starting from each stage of the product life cycle, resource extraction all the way to recycling. What's being extracted, what's being emitted into the environment, resources being used, etc. And then you then go to this life cycle impact assessment where you look at the impact according to a number of different categories. Climate change being the one that a lot of us are probably most focused on at the moment. You've got eutrophication, land use change, really, resource depletion, acidification, ozone depletion, ecotoxicity, ionizing radiation, and so on, human toxicity as well. And there are other categories as well, and this is just a kind of snapshot of what we mean by what are the impacts in specific areas, and this sort of helps you to quantify sort of impacts by separating them into categories. And then your interpretation is the sort of, after you've figured out what happens in each of these things, what does it really mean in terms of, for example, human health, ecosystem health, and natural resources? Is this dangerous? Is it not dangerous? Is it acceptable? Is it not acceptable? As I said earlier, I think we come to this quite often hearing about LCA, and particularly in the context of climate change. And for those of us in shipping, particularly in the context of shipping's GHG emission reduction. But as you can see, that's really only one of the categories that you could actually use an LCA for. And generally, an LCA is holistic, so you really want to look at all of these things all at the same time. Here's an example. So a different way of looking at it, the scope, which we talked about as the first phase of an LCA, includes the definition of a system boundary, which is this sort of block around it. This defines which processes we include and which we exclude from the study, and this follows on from the goal. And this, as you can probably imagine, is quite important as a sort of starting point to sort of figure out what actually is going to go into this LCA. So in this example, waste and recycling is within the system boundary, while for a different LCA, these might actually be excluded. And this brings into the whole thing about actually, it's often very difficult to compare one LCA to another because the basis, the system boundary, and the assumptions, the methodology, they're all different. So always compare LCAs with a lot of care, or maybe not at all. From a ship perspective, these differences might mean, in this case, one LCA might include ship recycling in their boundary, another one might exclude it. And of course, the system boundary could also include geographical or time limits, and these also have an impact on the final sort of result. Think about in terms of, let's say, the carbon intensity of the grid in particular countries, those which have lots of nuclear energy and those which rely on coal and so on. Now, the LCA is designed to be comprehensive. So as I said earlier, the more comprehensive you are with lots of different categories also means you can find the trade-off. So if you didn't look at all of them, you only, for example, looked at climate change, and your whole sole purpose was to drive down the climate change impact, you might be increasing the impacts in other areas. And unless you've addressed that and you've assessed that, you wouldn't know. It's also a relative approach, which is structured around a functional unit. And this functional unit defines what's being studied, and all the subsequent analysis are then relative to that functional unit. Now, this is a bit abstract again. What's a functional unit? Lighting 10 square meters with 3,000 lux for 50,000 hours with daylight spectrum at 5,600 Kelvin. Now, this is very specific and, of course, probably not relevant to a lot of us, but in some ways, the more specific you are with a functional unit, the more valid the comparison. Now, over to shipping, one study I looked at said, the functional unit will be transport of 1 ton of bulk cargo over 1 kilometer over a 20-year life cycle on a bulk carrier. HyMeth ship, which is sort of a project quite similar to us, but looking at recycling CO2 on a ship into methanol, their functional unit was a return voyage with a RoPax between Gothenburg and Kiel. Ours, which Camilla will talk about very shortly, is 1 kilometer of crossing during an assumed ship lifetime of 30 years. And the route doesn't particularly matter, but in this case, our route's Orkney, in Orkney between Kirkwall and Chapel. Now, LCA does not predict absolute or precise environmental impacts. It's relative in nature, and this is quite an important thing to grasp. So it's a relative expression of potential environmental impacts to a kind of reference in our functional unit. And you're integrating environmental data over space, not outer space, but over a geographical space and time. And there's, of course, inherent uncertainty in the modeling of environmental impacts. And some possible environmental impacts are future impacts. So this, in all of this, there are a bunch of assumptions and a bunch of differences that makes it, again, we really using LCA as a kind of relative sort of framework to compare sort of different things, but trying to keep assumptions as common as possible. So exactly this. In order to be comparable, assumptions must be the same, but then there is no actual single method for conducting LCA. So that's 14040 and its associated ISO standards provide a framework for how you should do it, but the precise methodology about what you should do and how you should do, and what you should do, what you should include, what you should exclude, is left to the individual to decide for each specific case. At this point, I'm going to hand over to Camillo to take over, and he'll take over request control. There you go. You've got control, Camillo.
Okay, perfect. Thank you very much. I would like to continue with this point because well, we're talking about shipping, and of course there is the IMO, which is for that for that sector responsible. So there are already some established methods for measurement of especially energy efficiency, which in practice are also linked to CO2 emissions of ships. I have here a list. I hope I can show it. I don't know. Now it's a bit slow. So we have the energy efficiency design index and the operational indicator, and then the two other indicators were recently introduced. So we have the existing ship index, and there is also the carbon intensity indicator, which is rating ships from A to E, depending on how efficient or how low their emissions are, and putting in place some measures to reduce that. I think it's probably better. It's taking too long.
Here you go.
Okay. Yeah. So all these methods refer to the fuel consumption during the operation of ships and the gases from the engine exhaust. But it's working with the keyword. Sorry for that. But these impacts are mainly tank to wake. I will explain what that means in a second. And usually it's only CO2. So this is more or less a traditional picture of the CO2 emissions. We have the operation in blue, and to the right, we have other life cycle phases, for instance, shipbuilding or maintenance or dismantling. So this is true, especially with fossil fuels, because well, the operation is the phase with the highest impact, especially CO2 or climate change impacts, but there is a catch. As we want to substitute the fossil fuels by alternative fuels, and that's the main strategy we have in the near future, there are some limitations because synthetic fuels are not per se green. Most of the impacts for the production of these fuels occur in the upstream, for instance, hydrogen, ammonia, and methanol, and not in the tank-to-wake part of the life cycle. There is also the need of CO2 and nitrogen for producing, for instance, ammonia or methanol, and hydrogen, of course. And we're also attempting to use new propulsion systems using technologies like fuel cells, and that's the case of HySeas. And those technologies can also have considerable environmental impacts. So yeah, and we might have impacts in other impact categories, as Ed already explained. So I have here one example. Let's say we are using methanol, and we are using a combustion engine, and here we have some CO2 output or exhaust gases mainly. We also have water. Of course, we have useful work for the propulsion of our ship and heat. And the traditional picture for producing methanol is like this. So we have natural gas and we have water. With that, we produce synthesis gas. And then in a reactor, methanol is produced. And then that's distributed, transported, and then could be used as, bunker into a ship, onto a ship. And of course, we have CO2 outputs in each of those life cycle stages or phases. But this is the traditional way. And if we want to try alternative fuels, we would have to use a different path to produce methanol, not using natural gas. So we would have something like this again. That wouldn't be changing, but probably we can use electricity, just as one example. And for that, we have CO2 capture here. That's why it's now green. It's an input, not an output like this part here. But we also have to consider the electricity, and the electricity has to come from any source. And that can also have CO2 outputs. And that's to say, yeah, we need to consider also the impacts upstream because, yeah, this is a balance. So we have outputs and an input here. So if we only consider this part here, we would be neglecting, and that's what this here is saying, we would be neglecting the well to tank part. That's how it's usually known. So that's why we need to consider the whole life cycle. That was just one example with methanol. Now, generalizing a bit more, we have the tank to wake part. I've also seen a tank to wave, but never mind, it's the same idea. And then we also have the well to tank part, where we have material production. In this case would be the fuel. The production of the energy carrier can be any of the alternatives. Then, of course, we have a transportation part. And that's what we call the well-to-wake life cycle. So here, you can see here the acronym. But in parallel, we also have the ship. And the ship also has a construction phase. Well, first, the raw materials. So ships are mainly made out of steel. There are some exceptions, but some are made of aluminum. But we need the materials. Then we have a production phase. Also during the lifetime, we have maintenance, and then of course have to be processed at the end of life. And if we consider all that, then we have the complete life cycle. There is even, well, some people even argue there is an additional dimension to this. You can add more things to the analysis. So you also have infrastructure, and that could be the ports, could be also the bunkering infrastructure. But yeah, for the moment, let's keep it like that. But the message is, it depends, and Ed already mentioned that, it depends of your scope. If you include more or less, can make your analysis more complete, but for transparency, you have to somehow mention what you are including and not including. So some of the advantages of LCA in comparison with the other methods to kind of wrap up this section it can have a higher explanatory power that goes beyond the operational phase and also including all the life cycle phases or some of them. May also include the fuel supply chain and infrastructure, and may consider environmental impacts beyond climate change. And that's important. Climate change is the main driver for implementing many solutions in shipping, but is not the single or only impact category. Something to mention, there are other life cycle thinking methods. So we can also, it's not only about environmental impacts, can be also about economic impacts. So for that we have, for instance, life cycle costing. There is also, let's say, a brother or sister method called social life cycle assessment, and there you can also assess social impacts, and this can be integrated to perform a holistic assessment. Now everything comes, so not yet. Just to mention, there are more impact categories. You can see here some of them. Ed already mentioned some related with the European guidelines. This is just one impact assessment method. So it's a set of impact categories, but it's not the only one. This again can give different results depending on what you use, and that's why you have to state which family of methods are you using. And now the disadvantages. The comparison between the studies is not always possible due to different goals and scopes and functional units and assumptions and background databases, the software used for calculating the impact and so on. So there are several things that can make analysis completely different. The validation is difficult because, well, and I think that's also a topic for shipping. In many cases, emissions are not directly measured. So when you have a broader view, it's difficult to validate what you get with this approach. Transparency, it's a topic because behind the analysis there is a lot of data involved. So yeah, that's also, well, the practitioner should mention most of the things he used because otherwise will be difficult to reproduce the results and will be difficult in the future to use them and compare them. LCAs cannot be used in all the situations, and this is something I should clearly state. LCAs are not risk or hazard assessments, so I can't assess what's the impact of one ammonia tank breaking in the middle of the seas. That's not the purpose of LCA. It's more to have a general overview of the environmental potential impacts. But for this situation, as the one I mentioned before, there are risk assessments or hazard assessments. And some impact categories are still immature, need more work. I mentioned here, for instance, noise production. There is some people working on those topics, or applicability is difficult. So for instance, abiotic depletion, there is a typo there. For these categories, there is still some lack of research, and yeah, but yeah, there is work on that. Okay, that was, yeah, and the data requirement is higher compared to other methods and the indicators I showed before. Okay, with that, I leave some room to Ed to go back to the presentation.
Before I go to IMO stuff, does anybody have any questions they want to ask at this point, given this sort of run through of LCA and ISO 14040? Either type in the chat or unmute yourself and ask your question. Don't be shy. No, it was so clear. Everybody fully understood, or everyone is maybe an expert in 14040. It's great. Okay. So a few slides on where the IMO is and where it's possibly headed. The current IMO legislation is based only on tank-to-wake and combustion products, really. CO2 only for greenhouse gas, not any other greenhouse gas, and then NOx and SOx for air quality. The framework is really designed to drive improvements in energy efficiency. The fact that it has some account of the carbon factor of alternative fuels is almost a sort of accident or byproduct of what the framework was originally designed to do. And so it doesn't do transition to alternative fuels very well. So what do I mean by that? We're unable to recognize certified biofuels that release CO2 in combustion. No accounting for methane slip. We can't distinguish between green ammonia and other shades of ammonia. So we ultimately present obstacles to a fuel transition because we're not able to distinguish good from bad. Some we can distinguish if you have something that doesn't have CO2 in combustion against something that has CO2 in combustion. That's about it. It's a bit rough. And I think by and large, there's a recognition that the well-to-wake perspective is a possible solution, i.e. something with LCA, something that takes a wider account of what is actually going on in order to kind of then have something to sort of distinguish between what's a desirable fuel from a GHG perspective and what's perhaps a less good idea, and perhaps also for policymakers to incentivize the better fuels. Better being a little bit subjective, and it, again, depends on what impact category we're looking at. Now, some of you are familiar with how the IMO works, some of you maybe not. So the IMO has a number of committee and subcommittee meetings, and then they have some intersessional working groups. So we meet together, and we have discussions based on submissions of documents to the IMO. The most recent one, which was held in March, is called, it's a bit of a mouthful, ISWG-GHG, meaning Intersessional Working Group on Greenhouse Gases, the 11th session. This was held in March, and a lot of time at this session was spent on talking about how should we use LCA for shipping. So, and this session broadly adopted a document called ISWG-GHG 11/2/3, 2 being the agenda item in question, and 3 being the third document of the second agenda item. This was a submission from the EU member states and a number of other countries, which broadly set out some principles for how LCA guidelines would look like, and how this might not be used, but actually how this might be calculated. There are lots of holes in this, and it's by no means a finalized document, but it serves as a base for discussion. And when what we say base for discussion, we will further discuss and develop this in a intersessional correspondence group, meaning there'll be sort of rounds of discussion that will be kind of coordinated with the hope of further developing this to something that eventually will be adopted as a guideline, as a standardized guideline at the IMO. And this correspondence group will start post MEPC 78 in June and run for a few months and report to MEPC 79. Now, in this document, it suggests that tank-to-weight values are kept consistent with the current IMO carbon factor values that we use for the existing regulatory framework, but we'll add some slip factors to deal with methane slip and 2O slip. And the concept here is to calculate these in accordance with IPCC guidelines. On the well-to-tank part, because you need the well-to-tank plus the tank-to-wake values to get your total well-to-wake carbon sort of footprint concept, the well-to-tank values are proposed to be based on LCA. However, the precise methodology and the level of detail and granularity is actually still to be decided. Now, you will notice that where we started ISO 14040 was this kind of broad guideline and framework that looked at all sorts of impact categories. What you notice in the IMO discussion is that there's already some deviations. So we focus on certain GHGs only. It's a single category impact assessment that make up CO2 equivalent. And then instead of then looking at all the other impact categories, the categories are, and looking at them quantitatively, in the IMO system, we're now thinking about having other categories reflected as sustainability criteria. So not necessarily quantitative, but actually more qualitative and even subjective. Because the focus actually at the IMO is on the fuel life cycle and not the ship. And it really is purely about GHG, with a kind of nod in the direction of the other impact categories. And of course, the functional unit and system boundary is actually not really fully defined at the moment. So there are few areas where, although we talk about ISO 14040 as a methodology, what we're actually doing is it is a kind of an LCA, but it is somewhat different from how we traditionally or normally seem to be using LCA. Now, a document worth reading, if for those of you who have access to IMO docs, for those of you who don't have access to IMO docs, it's worth registering for a free account and see if you can get hold of this. And if particularly anybody wants a copy of this, just send me an email, I can probably send it to you. But ISWGHG 11/2/5 is a study on sustainability criteria and life cycle GHG emission assessment methods and standards for alternative fuels. It's highly recommended reading, because what they've done is they've looked at 12 different standards, analyzed them or evaluated them, and then shortlisted 4 for further comparison. And what they excluded were general LCA standards like 14040 that didn't have any specific guidelines on fuel pathways, as well as tools or databases that don't really strictly define a calculation methodology. Just because if the methodology and the guidance isn't strict enough, you'll end up having very varying results anyway. So it's very difficult to compare them. The idea was to get to a point where you were doing as much of an apples to apples comparison as sort of possible for LCA. So the 4 that they ended up with was the GREET model, which is a kind of US model for this sort of assessment. The EU RED II policy directive, the HySeas certification scheme, which is what the airlines have been using, and then the JEC well-to-wheel study, which is again part of the EU's or EC's joint research JRC work that has been ongoing for a number of years, and this methodology is implemented in a number of EU instruments. With these 4 shortlisted standards, the case studies were then devised to compare the methodologies using common assumptions. The idea here being to try to figure out what would be the difference in results if you use different methodologies. Results were interesting. So you can see they looked at 3 different fuel types: green methane, blue ammonia, soy HVO. And you can see there's actually main difference tended to be with the well to tank part. Here for green methane, it's not overly substantial, but there are kind of obvious differences. For blue ammonia, almost no difference. But then when it came to biofuel, you could see quite large differences between the methodologies. One of the reasons for this is down to how land use change is modeled or dealt with. So land use changes, if you change some land from forest to growing, in this case soy, or growing something somewhere, and it means you have to displace, growing biofuel crops in one place means you have to go somewhere else and cut down some trees and then grow other food crops elsewhere. So land use change has quite a large effect, but there's also quite a lot of uncertainty in how land use change is quantified in terms of CO2. And then there's something about handling of co-products. So we had a discussion with Camilo about this. If you have a process that gives you more than one product, how you assign the CO2 footprint to each of the products differs. So in a good example here for HySeas is if you've got, in this case, we have our functional unit is the ferry, and the ferry is carrying both freight and passengers. And your how much CO2 do you assign to the freight? How much CO2 do you assign to the passengers? And you can repeat this across all the different processes where there's some difference or there's a number of byproducts. So in the creation of biofuel, for example, you have the useful stuff, which is the fuel, and then you might have some kind of low grade leftover stuff from the chemical process that could be used as fertilizer and stuff. Now, what do you assign to each of those categories? And the different methodologies appear to make this assignment differently, which then results in different results. Now, another very interesting thing that the study highlighted was some input assumptions have significant sensitivity to, or have a significantly large impact on the final result. One of them is grid electricity. What's the carbon intensity of the grid where you are, or in the assumption? And of course, whether you use global warming potential on a 20-year time horizon or a 100-year time horizon. So taking the second one first, for example, methane has a, depending on what read, global warming potential of about 30 on a 100-year time horizon, and something like 86 if you're looking only at a 20-year time horizon, meaning that the short-term climate impact of methane is much worse than the longer-term one. Now, the other one is the grid electricity here. So the assumption here is if we used EU average grid carbon intensity of 200 grams per CO2 equivalent kilowatt hour, you'd end up with this sort of emission level, gram per CO2 equivalent per megajoule of this. If you assumed that you had a grid that was mostly driven by solar PV, i.e. in a sort of perhaps in a desert or somewhere, with 20 grams, so basically a tenth of the carbon intensity per kilowatt hour, then you would have a substantially lower sort of value. And of course, if you had, if you had solar PV only and nothing else to back it up, and you also, this is kind of the holy grail, 0 CO2 equivalent per kilowatt hour, then you'd have a vanishingly low low value for this. But when you put this back into real numbers, if you assumed that your grid was 200 grams per CO2 per kilowatt hour, it would mean that eLNG would have 50% higher well-to-wake emissions than fossil LNG. So there are two takeaways here. One is your assumptions matter, and your choices matter. So what I mean by that is your assumptions matter, is what you put in the model seriously affects your results, and what you decide to do as a result of doing your LCA also matters. So in this instance, if you know that your grid is not decarbonized, it's a bad idea to start at that point production of large amounts of e-fuel. You'd need to decarbonize your grid first in some way, or build wind farms or solar farms specifically for that in order to make it work. Otherwise, it's not a good idea. Right, I'll hand over to Camilla now on that happy note.
Great. Yeah, thank you for that. Now, the idea is to show some of the results we got from HySeas. First, a short introduction. Well, Ed already mentioned that, but
sorry, Lena has a question.
We'll maybe we can. Yeah, go ahead.
Yes. Sorry to interrupt. It was actually for Ed before we changed to this.
Okay.
Thanks for the review of the paper. It's a really good paper. I agree. Maybe it's a weird question, but there has been some discussion on how this use of green energy to produce fuel will, with all the associated losses of energy in between, if that's a good idea when you haven't fully electrified or made your grid fully renewable yet. So I was wondering if there's any sort of, like you have the indirect land use change, are there any speculations in doing something for energy as well? So you would have some sort of indirect energy use change if it became more, but if it was better for business to produce e-fuels than to produce green energy for housing. So you would sort of have the same amount of renewable energy now, use it to produce e-fuels, but instead we would heat our houses using coal.
It's a good question. Camilla, feel free to answer this, but I'll give it a go. I think what would need to be done there is probably for every government to do specific LCA studies with those scenarios to make those comparisons. because you wouldn't otherwise be able to decide. Because from a gut feeling point of view, everybody can say, "Oh, I think it's better to do this," but until you, I think, sit down and actually attempt to quantify what it would be better or not to do, and it's a very pertinent question. So you sort of sit here thinking, well, in this transition where renewable energy is sort of renewable energy is the amount of renewable energy we have is low carbon energy is constrained. What are we going to use it on? And I think this other part about the efficiency of the fuel pathways. So would you keep it electric, or do you then engage in all the losses to convert into e-fuel and back into energy again? Which is better? Is absolutely a good question. Whether anybody is going to take that holistic view is a different story, and I think you know my answer to that one. Camilo, feel free to add to that.
Yeah, I think you nailed one very interesting point. It's also a political one. How to decide which demand to cover with the resources or renewable resources available. I can't give a clear answer to that. There are pathways which are most or more efficient than other pathways. It's a matter of yeah.
Your Sankey diagram later, Camilo, yep. I think will help.
I was about to say that we have something about that just in a second. Can you still see me?
Yeah,
it's freezing a bit. Okay, yes. Yeah, because everything froze for a moment. But I can say because we also have that in our research, not for this particular project, but some people develop energy scenarios, and usually it's a normative scenario, meaning that they kind of decide, or the goal is already somehow decided in advance, and they try to find pathways which make that result possible. So yeah, LCA can be linked somehow to that, but it's still research. So that's what I can say. But it's a very interesting question. Okay, let me go back to the project. Maybe you find some answers in this part, hopefully.
Thank you.
Yeah, so I was saying, well, the goals of HySeas III is develop, construct, certify, and validate a hydrogen and fuel cell drive system. You can also, this is a bit of advertisement to the webpage. There is even a 3D walkthrough. You can have a look to the systems and how they were integrated. So that was the other part. We are mainly in the analysis. Develop innovative business models for ferry operators and coastal island authorities, and also encourage replication by disseminating exploitable lessons to the European and stakeholder communities. DLR, the institute where I work, contributed mainly with environmental, economic, and social and market assessments. So I'm going to show one slice of what we did. Okay, so here you can see the project partners from HySeas III, and you can also see here, well, we got support from the European Union. For this study, we followed this goal of comparing the potential environmental impact of a hydrogen fuel cell battery ship ferry with other alternatives like battery electric, a diesel battery electric, and also a diesel electric Ropax ferry, according to the designs and tests carried out in HySeas III. So that's more or less what we wanted to do with this assessment. To make it more specific, the scope, Ed already mentioned the functional unit. We consider 1 kilometer of crossing during an assumed lifetime of 30 years. With this ship, we have the issue that it transports, or she transports people and freight. So it's difficult to allocate impacts to each of those. And that's why we decided to to stay in 1 kilometer instead of using the unit of person kilometer or person nautical mile and ton nautical mile or kilometer. The location is Orkney, Scotland. The time reference is here. We used this Equinvent 3.7.1 as background database. The software we use for the calculations is called Brightway 2. The family or the impact assessment methods we use is ILCD 2018 as implemented in this software, plus cumulative energy demand. And we use this allocation model for the database and how we calculated all the impacts. How did we model this? So we have, for instance, here to the left, different ship components. We have the whole end structure. For particular alternatives, we have a diesel engine, an electric generator. We also have battery packs, fuel cells, and hydrogen tanks in the case of the hydrogen alternative. And these 4 alternatives, which I already mentioned. During the operational phase, we also have an energy supply. So we have diesel, for instance, here. Electricity, we assume the electricity from the UK grid, low voltage. And also for hydrogen, we assume production with wind, as is more or less the case in Orkney. There are several projects doing that. So for producing hydrogen, the electricity goes to a PEM electrolyzer. Then we have later compressed hydrogen, some storage, transport, and dispensing. All that was assumed. And you can see here the lines connecting for the different alternatives. So in the diesel electric alternative, we only have diesel. It's electric inside, but it doesn't have a connection to the mains. Whereas in this case, we can charge the batteries from the grid. And then we have the operational phase. And then at the end of the lifetime of the ship, there is some process to demolish the ship, basically. I already mentioned that the functional unit is 1 kilometer of crossing. So to show some of the results, oh, sorry, I was missing that before. This is how we model the operational phase. We took data from other product partners, how they model the operation in terms of energy inputs. You see here different loads on the ship. And this was used with different operational strategies to provide or supply electricity to the loads. I'm just showing one example here. So you can see the fuel cell is operating at more or less a fixed rate, and then the battery is also helping to do some peak shaving. And with that, we have at the end hydrogen, diesel, and electricity consumption. And that's what we use, especially for calculating how much hydrogen, diesel, and electricity was needed during the lifetime of the ship. Now, going to the question. Yes, we have this Sankey diagram. So here we have electricity, and that's the electricity input we would need for, well, this is done on a relative way. For producing hydrogen, the hydrogen we need for 1 crossing. And then after the electrolysis, we also have some losses and are quite considerable here. Then we convey or transport this hydrogen onto the ship, and then we have the fuel cells on board. And then again, there we have some losses, and that's what you see here. We also charge the batteries overnight, and also the fuel cells supply some electricity to the batteries during the operation. And then at the end, this is the energy we get into the propulsion system. So you can see the losses are considerable. That's something we can't deny. There are some possibilities to improve this in the future here and also here. But of course, there are some thermodynamic limits to that. So it's a reality. There are important losses. yeah, but when we compare to, yeah, let's say the inputs of electricity and what we get out, this is what we get, the efficiency from electricity to electricity, because we can also have primary energy, and that makes it a bit more complex. You can see we are around 30%, in some cases even lower, depending on the operational strategy we use. Comparing this to other sources, you can see, yeah, here 27, 26%, and this is from Marin. They did some analysis about different supply chains and how much energy goes towards the end of the, or for the propulsion compared to the inputs. So you can see it's more or less in the same order of magnitude, close to what they analyzed. About the ship construction phase, what we used is some assumptions from the designs. You can see here some of the materials that were assumed for the construction of the ship, mainly steel. We also have glass, copper for cabling, just to mention some. And also for building the ship, we need some processes like welding, or also electricity for the facilities or the shipyard where the ship is constructed. And then we have some outputs. For instance, scrap. This output here is non-volatile, non-methane volatile organic compounds, mainly from paint. So were some assumptions. Of course, this is limited compared to a real environmental analysis, but it's the data we have. And with that, we kind of built our hull and structure, and then we added the specific propulsion system. And then we have the ship construction for each of the alternatives. Okay, now going to the results. First, I would like to present the cumulative energy demand. The comparison is more relevant than the values. You can see here that hydrogen is the alternative with the highest cumulative energy demand. There are some efficiency losses, as you saw before. And then also you can see here, well, the end of life is barely visible there, but the construction can be seen here at the bottom. It's not that relevant compared with the operation, but it has some contribution. The other aspect I would like to mention here is, well, for the hydrogen and fuel cell battery alternative, we have the input of wind power here. It's the main contributor, thanks to the assumption we did before of using wind power to produce hydrogen. Also, the inputs from the grid make some fossil fuel contributions here. So that's also visible here. For the alternatives using diesel as fuel, you can see that most of the energy is actually coming from fossil fuels. And then the battery electric alternative, we assume charging from the grid. So you can see some fossil fuels, nuclear in the UK, for instance, and then some other contributions from renewable energies and biomass. So in this case, the alternative is mainly influenced by the choice of the UK grid, and it's more or less showing the mix there. Let's see if I can go to the next slide. We also analyzed the hydrogen production, and you see here, for instance, alkaline electrolysis, PEM electrolysis. So there is some difference between both electrolysis technologies. We also see the comparison with steam methane reforming, and what you see, the vertical lines are actually the electricity emission factor for different places or different countries at low voltage level. So the main message here is, if we go to the left, you can see some countries here. Norway has, for instance, a hydropower cell capacity, which provides, if I'm not wrong, more than 90% of the electricity So that's why you see a so low result here. If we go to the right, then after this region here, producing hydrogen with electricity from the grid, is actually producing more emissions upstream, but it's producing more emissions than steam methane reforming. So we need to use renewable energies. Well, some people also have an important nuclear capacity. I'm not getting here into the debates, but the message is if we go to the right, there is a point where we actually produce more emissions than using steam methane reforming to produce hydrogen. So yeah, that's what this plot is mainly showing. And then when we analyze the particular situation of our project, this is what we get. We can reduce more or less 81% CO2 equivalent, not just CO2, but CO2 equivalent emissions per kilometer in comparison with a diesel electric ship, which is this one here to the left, as long as hydrogen is produced with wind power. If we produce it with any other electricity source, this can change, and I will show somehow that analysis. We also have here the battery electric alternative, and there the higher efficiency helps a bit, and that's why we have already reductions using the UK grid, but are not as considerable as in this case. And well, using batteries like a hybrid ferry helps to reduce a bit the emissions according to this analysis. This is just to show that we also assume during the lifetime some changes of fuel cells and batteries. That was also assumed, but they have a minor contribution, and that's why you don't see a straight line here. So that was also assumed, yeah, during the lifetime. I will skip those details. And here is where you see the effect of the emission factor for hydrogen production on the climate change cumulative emissions. And that's, well, this is the base case using wind power. And then when we start to increase the emission factor of the electricity used to produce hydrogen, then the impact starts to increase. Here is the battery electric alternative. Then here is the diesel battery electric, and then here the full diesel electric alternative. So you can see once we increase the emissions from that particular grid, of course, the environmental benefit or the climate change benefit reduces. And at some point it's not anymore of benefit. We are producing more emissions in the upstream to produce hydrogen. And this is more or less where we start to be non-competitive with the other alternatives. As Ed and I and myself mentioned before, climate change is not the only impact category. Here you can have a 360 view of several categories. So you can see, well, in purple, it's actually our alternative in HySeas. You can see the climate change reduction here. There is some increases in other impact categories, and that's what you see here, these spikes. And each alternative has some categories where there is a higher impact. This doesn't mean that the impact is big, but it's comparatively big. So it's in relative terms, is higher than the other alternatives. It's not necessarily that it's big. That's also important to state. For instance, in these categories, is mainly related with the mining for the materials we need for new propulsion systems, for electrolysis, for the batteries and fuel cells in the propulsion system. And also, well, we need, for instance, copper for the batteries inside. Lithium-ion batteries are more copper and aluminum than lithium. So all those materials, we need to mine them, and that's why there are some increased impacts here in these categories. I also mentioned this can be extended to other methods. I'm probably already taking more than the hour, and this is the economic part. The economic part. So we also estimated some the investment costs for the ship. We have contribution of different parts, and that's what you see here. So we estimated at least that there would be a difference of plus 25% compared to the base case, which is the diesel electric ferry in this assessment. This can also, well, that's basically the capex of the hydrogen fuel cell and battery ship, but can also be extended to the whole lifetime, and that's what we see here. So we also included here the operation, and you can see here hydrogen also has an important contribution. The fuels in the other cases have a smaller contribution, and that's because hydrogen, well, in this case, we assume 9 euros per kilogram based on the location, the cost for electrolysis, the cost of electricity. Yeah, we also analyzed possibilities to see how this is competitive with the diesel alternatives. Sorry, I forgot to mention something here. We also, as I mentioned before, consider replacement of fuel cells and batteries, and that also makes a contribution here on top. So we included also carbon values. That's of what I have read. It's also a hot topic in the UK. So we included carbon values for the diesel and diesel battery alternatives, and that's what you see here. That kind of closes the gap between the hydrogen fuel cell battery alternative and the battery alternatives. We also included here some cost for the infrastructure if, for instance, batteries are required onshore, because that could be the case if you have a grid that can't withstand charging at 1 megawatt. The batteries, I don't know, 12 times per day. So you might need some buffer onshore, and that increases the cost. But you can see that closes the gap. Still, there is some gap between this alternative and the diesel-based ones.
Camilo, just to clarify, carbon values, you mean the kind of UK ETS, sort of carbon pricing, the carbon marketplace?
What we used here, we didn't use information from the ETS. What we use is the Green Book of public procurement in the UK, and there are some suggested curves from 2020 to 2050. I think even 2100. So,
do you know what the carbon price was on this one?
I don't have that here in the slides, but I think it's close to, in the high scenario, it's close to 400 pounds per ton.
CO2. We're currently at 70 pounds, yep, I think, per ton CO2. Okay.
And here is close to 150, I think. But it's actually time variable, so it's not fixed at a value. It's every year has a value. So, yep. And also the electricity has some carbon value because it's also producing CO2. So that closes the gap, but there is still a gap. Probably the reduction of hydrogen cost in the future, as expected, or of the fuel cells and the shipbuilding can also contribute to close that gap. Okay.
Could you say something about 9 euros per kilo of hydrogen, whether that's sort of high, middle, low, and where you see that evolving, let's say? I mean, or at least what are some of the studies you've looked at?
Yeah, we calculated that cost, mainly using the electricity cost there at Orkney, well, assuming more or less 10 pence per kilowatt hour. For instance, if you only use renewables, and that's with wind energy close to 4 cents or 4 pence per kilowatt hour, then you can reduce the cost. I would say for the moment is probably optimistic, but it's going that direction. In Germany, we are located in Germany, and here we have hydrogen tanking stations. You can, in theory, purchase hydrogen for your hydrogen and fuel cell car for 950. So it's probably subsidized, but it's also produced with steam methane reforming, as far as I know, most of the tanking stations. So that gives also a benchmark. But the main factor is the electricity price. So that makes most of the cost, production cost. Okay, yeah. Finally, some conclusions. First, life cycle assessment is a compilation and quantification of the inputs and outputs of, and can give some information on the potential environmental impacts of a product system over the course of its life cycle. There are 4 phases defined in the standard 14040, definition of the goal and scope, the life cycle inventory, which is collecting the in and outflows, the impact assessment, quantifying the impacts on the environment, and the evaluation. For alternative fuels, we actually need also to include the impacts beyond the tank to wave or tank to wake approach, and that's why we need to consider all those impacts in the upstream. There are some existing indicators, but life cycle assessment can help to overcome some of the difficulties with those indicators, which only address tank to wave, basically. And we can also consider other impact categories. So, also important. However, we need more data, and that's not always possible. Comparisons are difficult, especially between studies, even between alternatives. The validation is difficult, and I already mentioned that life cycle assessment is not a Swiss knife. You can't use it for everything. It's not a risk assessment. Now, more about HySeas III. We can see that or at least we predict 81% reduction of the CO2 equivalent emissions for this hydrogen fuel cell battery alternative, as long as we use wind power for producing hydrogen. There are some impacts increasing in other categories due to, for instance, the production of fuel cells, electrolyzers, batteries, all the systems we need for this kind of ship. And the life cycle costs, at least according to our analysis, are higher for the alternative developed under HySeas III. Future higher fuel prices, for instance, diesel, and also the carbon values I already mentioned can close that gap. And that's more or less what I had to show. I also wanted to do some advertisement. We are writing this report. It will be one of the deliverables of the project will be public. So maybe for more information, hopefully it will be available within the next weeks. And that's what I had to say today. Some references, you can also check them later. And thank you.
Thank you, Camillo. And now it's over to our audience. Do you have any questions? Please speak up and ask them.
I did have a question. In terms of the resource that went into actually doing the analysis, I guess the first thing would be if you were to just ask a shipyard, to go and do that analysis for their boat, and you look at how in depth your analysis was, do you think yours was more than would be necessary, and how long did it take you guys, and how many people, person hours did it take?
Well, we got data from our project partner Simul. They gave us some bill of materials, what they estimated for this ship. I would say primary data from a shipyard would be always the best thing. In our project, we didn't have that chance. Yeah, there might be even some differences, regional differences. For instance, one shipyard in the UK, and also shipyards for different types of ships, because they are quite specialized. So I would say, yeah, primary data is the best you should use. We didn't have that, but we tried to estimate with some publications and the data we had. Regarding the effort, well, for the construction part, I would say we had to wait a long time and for getting that data, because well, design is an iterative process. So yeah, I wouldn't say we work all those years of the project in this. I couldn't say how many people. We were mainly 3-4 people involved in the project here, but doing different parts. We also do the economic assessment. We also had some inputs for the social assessment, which I didn't show here, market potential. So I couldn't kind of cut every part, but yeah, that's what I can say.
Okay. My practical answer to that question, John, is in the UK, the answer is probably no. For most of the commercial shipyards, they wouldn't be able to do it. They struggle to kind of build ships anyway. And I'm being very honest here. And they struggle to find people to kind of enough manpower and capacity within the shipyards just to do normal shipbuilding stuff, never mind do this. It is quite involved. I mean, the data and the information should exist. It probably exist in silos. The estimator should have some information about what he's procured. Whether it's centralized enough to be able to turn it into something useful is a different question. We have, I don't know, Mr. Lee, I don't know, would you want to share whether you think in Korea you're able to do an LCA analysis? You are muted, I think. At least we can't hear you. We can't hear you yet. Sorry to put you on the spot. We still can't hear you. Sorry. Oh, now you have muted yourself, and then if we unmute and maybe your microphone connects, we can. Let's see. Yeah, you're okay.
Sorry.
Yes, now it works.
Yeah, can you hear me? So
yes, we can hear you.
In case of Korea, so we also considering the application of the LCA. Even in case of in my case, so I drive the hydrogen car. So every times I check the CO2 emissions, and I ask the how to make the H2. In case of Korea, so H2, the making process is using the remaining H2 during the refining process. But in the Korea, it's now the better way, finding better ways, because Korea did now invest much money to make the hydrogen value chain. I'm very interested because our Hyundai company also develops the PEM electrolyzer, and we have already materialized this kind of the pure cells. And so we have already carried out the small boat size, the boat scale, the vessels, so to the materialize. Anyway, so it's very interesting project. So in the HCA also every day now the rulemakers has the interest in, even in case of me, so I'm participating in the Korean government advisory group for the MEPC and ISWGHG. Anyway, so this result will be very interesting and maybe very helpful to verify the CO2 emission as the environmental impact. However, the problem is this, as far as I know, the big resistance from the other side. So because the some part so would like the insist tank to wake, and some party so including European parties so insist that well to wake approaches. And even in case of ISWGHG 12, so I have read many articles, and some the document says the emission trading system is to be applied. So the submitted by the Norway, but the carbon pricing is a key factors to realize in the LCA and the environment to minimize environmental assessment. Anyway, so this is very interesting, the subject. So thanks for invitation, and so if there is chance, I would like the participate and so shares my idea with you. Okay, thanks
very much, Mr. Lee.
Yes.
Martin.
Hi, coming to John's question, specifically, it was me who invited DLR in to actually look at this. I think the simple answer to your question is no, it will not be practical for shipyards to go into such detail. But in the early days of evaluating this sort of thing, what I felt was that we needed to look at this very closely. What I would expect is we'll see a number of studies like this for different types of vessels. And then eventually people will have a general feel for what the effect of changing from fossil fuel to the renewable variants are. So Camilla came up with a figure of about 80% on a good day reduction of carbon there over the lifetime of the thing. And that was really the kind of number I was looking to get out of there. I would imagine different vessels will have different results, but I don't think we need to do every one of them in that detail. I think, you know, perhaps over the next 10 years, if we get 10, 15, 50 of these studies, the sector and government, and particularly policymakers, this stuff is more expensive, as Camilla pointed out. They're certainly getting started in it, newcomers to this sort of thing. It's going to need a lot of policy support. So one of the feelings I had was that it was absolutely essential to be able to demonstrate to policymakers in Europe, the UK and beyond, that this really did have major carbon savings and other sort of knock-on benefits. So I think in this case, we have gone over the score compared with what people would normally do, but it's providing that evidence base upon which policy and investment decisions can be made. So that was the thinking behind this, and that's why Camilla's giving this today. So I hope that covers most of the sort of bits and bobs. Right, thanks, Ed.
If you've got that, you must have something left over from that 206 million quid in UK shore that you might be able to direct in a particular way. Because this is, as Martin says, it needs to be done at some point, and it probably at government level, because that's for you to use to decide where the policy is going. Okay, enough putting you on the spotlight, John. Sorry about that. Vaidehi had a question in the chat: which emissions database was used for this study, and have the results already been published in a paper? Camille, I'll let you answer your colleague.
Yes, we use Equinvent 3.7.1. There is already a new version, 3.8. That was the main background database. We published before, that was a long time ago, almost 3 years ago, one study about LCA. It's available to anyone. You can check it. The results are slightly different. We use a different software solution for that, and also a different impact assessment method. But that was at the beginning of the project. So we first published this and then dig a bit more into the data we could get along the project. So you can also, I can share the link later, but that was published at the beginning. Yeah.
Yeah, thank you. That helps.
Okay.
Thank you. Benoit.
Hey, I just had a question. You mentioned uncertainties that are involved in the LCA because you need so much data from many different places. In the end, you have a result, you give a figure, which is really good, but I guess it's easy to manipulate as well. So I totally see how LCA can be used for marketing purposes when people are going to advocate for one solution or another by focusing on one aspect or another. So does your toolkit enables you to produce uncertainty value for this analysis?
I can. We were just discussing about this when we started the workshop. Well, calculating first, and I also told that to Ed. There is something. Well, it's let's say known uncertainty, and there is also unknowns. So you can kind of predict somehow the uncertainty. The tools provide. There is, for instance, something called pedigree matrix. So you assign, it's completely qualitative. It's a scale from 1 to 5. You assign in different aspects one of these qualitative values, and then with that you can assign more or less a probability distribution. And then you can run Monte Carlo analysis and see more or less your cloud of points or of results. That's possible, but the problem of that is that only tells you what you kind of assume it's your uncertainty, but you don't know what you don't know. So that's where, yeah, the method has some limitations, but any method has that limitation. And what I also told Edwin is that LCA is not perfect. All the models are wrong, but some models give useful answers. So we haven't done that here, but in principle, the tool we use can be used for do that kind of analysis.
Okay.
The main intention of doing that is actually see how much of that distribution curve overlaps, and then you can say with some confidence that there is a difference between the results of different alternatives, for instance.
Yep. Okay, yeah. Thank you.
This is in a way why we emphasize in the beginning this idea that it is relative and you try to keep all the assumptions as similar as possible when you're comparing across, and that you need to be transparent. And so all those things that are almost the prerequisite of an LCA, that it also enables other people to have a look at what you've assumed and what you've tried to keep constant. So you were kind of comparing apples with apples. So at least you then maybe have some at least control over the uncertainties because you've kept some stuff the same, and that uncertainty varies together. And then you have another bunch where they're slightly different, and then there may be some different uncertainties there. But this is almost, I mean, as Camilla was also saying, it's the prerequisite of comparing LCAs, that it's we're all upfront about what you've assumed. Yeah. Which you would never do in marketing, of course.
Thank you for that. Yeah.
I think you also had the question, maybe, I don't know if someone else has a question, but I can show you the carbon values reported by, I think it's just a second. Yeah, that's the, yeah, it's a Green Book of Procurement. Let me show my screen for a second. So these are the values, well, it's made out of an analysis from the IPCC, and we have 3 different scenarios: a low, central, and high scenario. And as you can see, the assumption, yeah, changes depending on the year. So we assume, since the ship was assumed more or less with a 30 years lifetime, then it would be kind of the integral of this function here, and also the output of CO2 from the ship. So yeah, you had that question, so I wanted to show you.
Thanks, Camilo.
Sure.
Great. Well, in the absence of any further questions, I'm going to close the meeting. Thank you very much for staying awake and following to the end. If you have any sort of questions, feel free to reach out. Otherwise, have a good day. Thank you.
Thank you. Have a good day.
Thank you.
All right, thank you.
Thank you very much.
Bye.
Thank
Have a good day.
you. Thanks very much, everyone.
Yeah, thanks, Edwin. Thanks, Camilla.